So, I want to give you a hypothetical situation. Okay, call your mind back to when we were doing like first principles and introducing gradient functions and all that in the first place. Okay, suppose I gave you a function, okay, and it has a y-intercept of 3, and when x equals 5 or something, I don't know, it comes up to, my scale's going to be terrible, 13. Okay, so that's thereabouts. Okay, now simple example, right? But suppose I wanted to know gradient. Okay, now it's trivial, I know, but let's just go through the process anyway. Okay, what's the gradient of this straight line? How do I work out gradient?
13 minus 3 over.
Gradient, the definition of gradient is rise over run. Yes?
What are they gradient?
Okay, rise over run. Right? So in this case, how do I calculate rise? Well, let's take 2 points. Okay, the points I've already given you are 513 and 0, 3. Okay, so what I'm going to get here is rise. That's 13 minus 3. That's how far I've gone up, and how far have I run across 5 minus 0. Okay, so I get 10 on 5. So my gradient is 2. Okay, now what could that tell me? If I wanted to draw the gradient function of this, it would be pretty simple, right? It would lead to, at 2, it would just be this straight line, okay? Because it's got a constant gradient, no problems. Okay? But what I want you to imagine now is let's try to turn this on its head in a specific example, okay? Now gradient being rise over run, okay? In some of the questions we've been looking at, the applications of differentiation, we've thought of this as like actual physical quantities. For instance, speed. Okay. Gradient is another way to say how fast is something moving. Okay. Now think back to like whatever, year 7 or year 8 science. What is the definition of speed? And how does it relate to rise over run? It's distance over time, right? Distance over time. Okay. Now so far, I've been thinking of this in these terms. Okay, dy dx. Okay. So in this case, working out gradient, I'm dividing by dx, okay? And that corresponds to dividing by time, if you like. Okay? But what I have in this Riemann integral business, right, is not division by dx, but multiplication. Now, what would that mean? Well, looking here, this is 2, okay? Rearranging this equation, right? If I multiplied through by dx, what you get is, let's see here, rise is gradient times run, whatever that means. Now that's a bit abstract, okay, and that's why I brought this speed, distance, time thing over, because this makes sense to us when you think about it in terms of this. What does dy, what does rise correspond to over here? Distance, right? Well, how do you work out the distance you've traveled if you know how long you've traveled and how fast you've been traveling? Well, distance, that's speed times time. Okay? So I've got something, I'm onto something here. Okay? I've got a y over here, and then got a gradient of some kind, right? So m, and dx. Okay, now this is helpful to me because it's not exactly the same, it's not rigorous, but it looks like something like the process we're doing here. Okay? So let me try and reverse this. Right? I'm coming from now this kind of situation. Right? So instead of knowing rise and run and working out gradient, I want to know speed and time and work out distance. Okay? So what I've got is, well, here was my gradient function, right? My speed function, if you like, and it was just that f dash dy and dx equals 2. Okay? Well, if this is my speed, right? That's my speed. Where's time on this? Where's time? Well, time is this way, isn't it? I should really write the time here. It's my time axis. Okay. So if I want speed times time, okay, and what I had before was 5 seconds, for instance. Okay. Speed times time here is just the area of a rectangle, namely this one. Okay, does that make sense? Now, obviously the area of this rectangle is 10. Now, what did that 10 signify in the last scenario we just had when we looked at it in reverse? Okay, where did that 10 come from? That 10 came from this scenario, right? From the 3 and the 13. Okay, does that make sense? It's the 13 minus 3. That's where this 10 appeared when we thought about it in reverse. Okay, 10 is 5 times 2. I should really say 13 minus 3, and this 5 is 5 minus 0 times 2. Right? Does this make sense? Sorry, wrong way around. Speed was 2. That's 5. Does that make sense?
No, that equation is correct.
It's all clear now.
Okay, now, here's the important thing though. 13 minus 3. That's kind of like a shortcut way of working out, instead of working out area, if I know the function that it came from, the function that I had to differentiate in order to get to this, right? Then I don't need to work out, well, if I wanted to work out area, if it was some weird wiggly thing, okay, all I need to know is where I start and where I end on that original function where I came from. Now, rather than saying original function where it came from, we have language for this, right? It's called the primitive function, right? So if you can know what the primitive is, then all you need to do to work out this weird area, if it's a weird area, right, is go to your primitive of this and just take your start and end points. That's all you need, okay? Now, how do we write primitive? We usually say if this is f, lowercase f, we call this capital F, right? So, here's a way to write it. If I'm trying to work out area, okay, under this lowercase f, okay, and if I know what the primitive is, if I know what capital F is, okay, all it is 1 point minus the other, isn't it? Where I start, where I end. That's it. Okay? So, what Reno was trying to work out, right, his weirdo calculations and all that kind of thing, and putting together these infinitesimally small rectangles, okay, was to say if you want to work out what an area is, you add up all of these rectangles. Then what you really need to have known from the first place is where the function came from, okay? And then all you need to do is subtract. That's all you need to do. Okay? Now we know that the process that we've called this process very deliberately anti-differentiation, okay? Because we're used to starting at capital F and going the other way, okay? But he called it integration because he was trying to solve a completely different problem. Okay, does this make sense? He's trying to work out an area. But it turns out these are the same problem. Working out area is the inverse of working out gradient, which is weird. I don't know if that makes sense to you. You're like, I want to know area. Well, I'll just undo gradient. They don't seem like opposites to me, like left and right. Like, what other, like square and square root, okay? But area and gradient are like that, okay? So, all that to say, why have we been doing anti-differentiation? What was the point of it? It's because what we want was area. Okay, does this make sense?